because A has, the back of the train has, so to speak, caught up a little bit with the beam of light, whereas going to the right, it actually has a bit further to go, because the train has moved away as the beam of light was going along. And see, if we were in Newton's world, then you would just say, well, all right, yeah, I get that the beam of light going to the right covered more ground, but I mean, it was also giving a boost, right? I mean, wasn't this faster light? I mean, after all, it was moving at, you know, c plus whatever the speed of the train was. But this is where Einstein said, no, there's something funny about the speed of light. The speed of light actually is the same for all of us. It's kind of funny, you know, it's called the theory of relativity, but when he first put it forward, he actually wanted it to be called, I mean, I forget the exact German word, one of you probably knows it, but it's something like, you know, the theory of this absolute thing. But then when other scientists, you know, read the paper and so on, it eventually came to be called the theory of relativity, and of course that's what we call it now. But one of these cornerstones of the theory is that the speed of light is the same for everyone. It doesn't matter if the person holding the flashlight is running towards you or running away from you. C is always C. It's 300,000 kilometers per second, approximately, and it's just the same for everyone. So you can't give light a boost. So now what happens? Now there's disagreement. Your friend on the ground, well, you, standing in the middle of the train cars, still think that A and B are simultaneous. But your friend on the ground disagrees. A came before B for your friend on the ground. You may also notice that the guy in the car has gotten thinner in the second diagram. That's not a mistake. It's just that one of the effects of special relativity is length contraction, and you'll think your friend on the high-speed train has lost some weight. But he'll also think you have lost some weight, so it's a win-win thing. Everybody comes out happy in that situation. Well, as I mentioned before, but just to repeat it, different observers can now disagree as to whether event A and event B are simultaneous or not. And as Einstein once said, there's no audible tick-tock everywhere in the world that can be considered time. Well, you know, Newton would be very upset to hear that, wouldn't he? This is the very opposite of what Newton had said about the world. Of course, what Einstein says agrees with all the experiments we've done. So unfortunately, we now have to give a failing grade to Newton for his definition. Well, of course, I'm being a little bit harsh. I don't think he deserves an F, maybe just an A-. Really, his book is quite excellent, but he has to go back and work on his definitions a little bit. All right, well, I'm just kidding around. But it's startling. I mean, what Newton said about time seemed so intuitive. I mean, it's so hard to imagine that. I mean, how could that definition have been wrong? I mean, what aspect of it was anything less than just common sense? But our common sense turned out to be not quite right, as Einstein showed. So we have to chug along because there's a couple of other little topics to cover. Some other implications of Einstein's theory, in this case the second part is his general theory of relativity, his theory of gravity. His theory suggests or shows that we have a dynamic universe where things don't always have to have been as they are now. In fact, it suggests that the universe is either expanding or contracting. And when Einstein first noticed that this is what his equations were showing, he was kind of upset and shocked, because everybody in Einstein's day imagined that the universe was more or less static. So he put in this kind of fudge factor into his equations to make the universe kind of stable and static. But actually, just a few years later, Edwin Hubble and others who were looking at distant galaxies noticed that the galaxies are doing something a bit strange. They're receding away from us. And the artist who drew this funny diagram, I stole it from one of these old Time Life books. I think it was called Universe, and it's from, like, I don't know, 1972 or something. So if you have an old book collection, you might know the book I'm talking about. But what the artist has done is he has superimposed these spectral lines, these spectrums, onto each picture of the galaxy. And when astronomers look at these distant galaxies, the spectrum gets shifted towards the red end of the spectrum. We call it a redshift. But basically, it's analogous to the Doppler shift that we notice all the time. If you have an ambulance speeding away from you, it gets lower in pitch, but of course the ambulance coming towards you has a higher pitch. And this is an analogous thing with light instead of sound. And the implication of that is that, you know, sort of roll the film strip backwards, and these galaxies all must have been quite close together a long time ago, and eventually we got to this idea of the Big Bang, originated by various people. A Belgian priest named Lemaitre actually was quite crucial, was one of the first person to kind of express it this way. Well, okay, this is a new idea. And in fact, it goes back to the Leibniz-Newton thing that I was talking about earlier, because now you have these questions to ponder. What came before the Big Bang? Did time exist? I mean, whatever you think time is, it's pretty straightforward to say, well, it's whatever you think it is now, it has been that since the Big Bang. But, okay, what happened before the Big Bang? And I'm sure this is a question that cosmologists and physicists are always getting asked, and people would give lectures something similar to the one that I'm giving now, except, you know, from a real scientist. I'm just a journalist. But someone will put up their hand at the end and say, well, I want to know what happened before the Big Bang. And of course, that's a very difficult question to answer. There has been, of course, speculation, and there are different sort of ways to tackle that question. One of them, which some people might see as a bit of a dodge, is to say that, well, time isn't defined, and analogous to the way that, north isn't defined when you get to the North Pole. There's nothing north of the North Pole, and you could say, well, there's no time before the Big Bang because time just isn't defined. And, you know, with regard to the North Pole, it's not a dodge. It's actually the correct answer to the question of why, what's north of the North Pole, is that it's really not a proper question. Because when you get to the North Pole, sure enough, every direction is south, at least with regard to the surface of the sphere that you're standing on. So it's not, there's no mystery land north of the North Pole that if you work just a little bit harder, you'll discover. I mean, the world just ends there. And if you think there's something further north, then you don't understand what the word north means. So that's fine. But if people say this about time and the Big Bang, maybe, perhaps, the questioner feels they've been cheated a little bit. There are other approaches. Maybe time emerged from something. It's not quite clear what that something would be, but today's particle physicists, this is something they talk about. Experiments at the Large Hadron Collider, when they get it up and running again next spring, may give us maybe some hints about this. But this is the very frontier of physics, so we don't know exactly what this, some kind of quantum foam, something very fundamental, something more fundamental than time and space, from which time and space somehow emerge. But this really remains to be seen. Or, alternatively, maybe